with the lecture of Gianguido.
So, given the reaction to the at work part of supergravity that I did yesterday, I changed a bit the order of things, and I will discuss today something that has more to do with the structure really of supergravity theories, and which will allow me to go to extended supergravities in a simpler way. Also because this is a topic that is obviously of obvious importance, not just for supergravity. We will see something, if I manage to do so, of how this is important also for black holes, but especially it's important to think about supergravity as effective theories of string theory. And what I'm going to talk about then is are dualities. And you will see that these are indeed something, relations that are different from ordinary symmetries. And one of the important things about supergravities is that you can learn about dualities, string theory dualities also, from their effective theories from supergravities. Supergravities will have certain relations that allow you to equate different theories, essentially, to relate different theories and show that they are equivalent. And these dualities that you find in supergravity, and what I will show you today, of course, is a classical duality. So all the parameters are going to be continuous. Go to string theory, such parameters, and you will have restrictions. But still, you will find relations among different theories, which are somehow the result of taking string theory, for instance, and compactifying string theory on a certain manifold and reducing to 4 dimensions. So these dualities that we see now and that we will discuss in 4 dimensions are related to the dualities that you will see or that you can study in theory. And often you learn about properties of string theory, non-perturbative properties of theory, and these duality relations are among these non-perturbative properties, by looking at the effective theories, by looking at supergravities. Okay, you learn first what happens in these effective theories, and then you understand how to make it work at the level of the fundamental theory that is string theory. I will actually start from a very simple form of duality, which is the electromagnetic duality, because this is really what interests me in as a first relation in 4 dimensions, also because this will have a very strong impact on the structure of supergravity theories in 4 dimensions. What is the idea? The idea is that if you look at the electromagnetic Lagrangian, where you know that the field strength F mu nu, this is an abelian now gauge field. I'm talking about electromagnetism. I'm talking about abelian gauge fields when I will generalize this to an arbitrary number of gauge fields. This field strength satisfies, of course, the Bianchi identity, which you can write it like this, or if you wish, you can replace this antisymmetrization by a contraction, of course, with the epsilon, the Levi-Civita symbol, directly like that. And you know that you get equations of motion, which are like this. Now, the interesting thing here is the following, that if you look at the Bianchi set of Bianchi identity and equations of motion, as you know already from electromagnetism courses, you can essentially switch one into the other by defining the dual of the electromagnetic field. Now, if I introduce a dual electromagnetic field, which is 1/2 the epsilon tensor contracted with the electromagnetic field, then you see that the first relation that I wrote is the same, since it's equal to 0, it's the same as this relation. You see that if I introduce F twiddle, the dual field strength, the equations of motion and the Bianchi identities have exactly the same form. And you can decide whether you want to write them in this fashion as equations of motion, or of course, I can take the dual of the dual and write them in the following fashion, meaning as Bianchi identities okay, it's the same thing. They are the same equation. It's just a matter of how you want to write it. And this is somehow nicer if you want to write these things in terms of differential forms, because the first equation tells you that F is closed, and the other equation is telling you that the dual of F is closed. Okay. So clear that if you look at this equation, the set of Bianchi identities and equations of motion, you can take any linear combinations of them, and then you still have the same set of equations. So meaning that if I take some matrix acting on F and the F dual, and I define some new F and F dual, this satisfies the same set of equations. So the equations of motion and Bianchi identities are invariant under generic linear transformations like this. So the physics doesn't change essentially if you exchange electric and magnetic fields. Of course, you have to interpret the equations you get, but essentially you can switch electric and magnetic field. You send the electric field into the magnetic field in minus the electric field, and the set of Bianchi identity and equations of motion remain invariant. And you can actually make it more general, as I said, and take linear combinations in principle, and still it would be the same. The interesting thing, though, is that this is indeed a symmetry of the equations of motion and Bianchi identities, but it's not a symmetry of the Lagrangian. So this is not a symmetry in the usual sense. Besides the fact that I'm not acting directly on the fields, I'm not writing down some symmetry on the field. No, here I will have one field, a certain vector field, and I don't know, the gauge transformations, for instance, are transformations of this type. No, you act on the field itself, and this transforms. Whereas here we are talking about transformations of the field strengths. So it's not an actual standard symmetry, and it's not even a symmetry of the Lagrangian. The Lagrangian is not invariant. But the equations of motion and Bianchi identity are invariant. So essentially you have to think of these as field redefinitions, which however let you express a theory in terms of the degrees of freedom of another theory. In this case, it's a trivial redefinition in the sense that you're simply mixing up electric and magnetic fields, and you can trade, though, in this way, a situation in which you are discussing how, for instance, certain electric and magnetic fields are propagating with certain conditions, certain boundary conditions, into a different problem in which you have switched the electric and magnetic fields, okay, in the appropriate way. So the idea is that these field definitions are useful because the Bianchi identities and equations of motion remain invariant under these field redefinitions, and therefore it allows you to go from one theory to another theory, of course, changing, if you have charges, the meaning of the charges, changing the boundary conditions, but essentially translate a problem that maybe is difficult in one set of coordinates, let's say, in one set of fields, translate it into another set of fields where the problem becomes easy. For instance, imagine that, now this is a very simple case, but imagine that we can do something like this, but more complicated setup. And we know that we have a problem that is very difficult to treat because it's non-perturbative. You have a coupling constant that is very strong. If the transformation that you're invoking, like this duality transformation, is a transformation that sends one charge into the inverse of the charge, one coupling into the inverse of the coupling, then that your problem that was non-perturbative in certain, if you use certain degrees of freedom, becomes perturbative using the other degrees of freedom. And so an answer that you wouldn't know how to find in one setup, you can find in the other setup. And then since you know the transformation that you have to do in order to go from one to the other. This allows you to find a solution and then understand what happens in the original theory. Now, in supergravity, this has striking effects in 4 dimensions in particular, where this is true, because clearly in 4 dimensions you have that a 2 form is dual to a 2 form, no? Is dual to itself. If you change the number of dimensions, the type of form that are self-dual or anti-self-dual will change. In 4 dimensions, a 2 form can be dual to itself, and therefore that's how you can get this kind of relation. But this has a very strong impact on the couplings and the interactions that you can have in a supergravity theory, and actually more in general, in any theory coupled to abelian vector fields. And this is very important. In fact, the first part of my discussion here has nothing to do with supergravity. The first part of the discussion that I'm going today has to do only with a gravity theory coupled to vector fields and possibly scalar fields. Okay, and in fact, in the original paper by Gaillard and Zumino, that's really a striking and amazing paper where everything is done, and a big part of the paper has nothing to do with supersymmetry. It has a very strong impact on supersymmetry and on supergravity theories, but this is something which has to do only with electromagnetic duality at this stage. So imagine that you have an electromagnetic Lagrangian, I mean, that you have electromagnetic field. Imagine that you have a certain number of abelian vector fields. I insist on this because this is actually the crucial point then that will change later. So I will have a certain number of vector fields and their field strengths, and assume that I have a certain number of scalars and possibly derivatives of the scalars. The restriction that I'm doing here is that I want gauge invariance, so I will have only, and I have abelian vector fields, so I will have the vector fields will appear only via the field strengths, so they will never appear naked. I will always have F, I will never have mu, if you wish. I will never have a mu appearing. And then I have a Lagrangian which has at most 2 derivatives. Okay, then you can discuss extensions with higher derivative terms, but I'm discussing low energy physics, so I'll keep 2 derivative terms. And I can write down a generic Lagrangian. The generic Lagrangian can be split in the following way. You can have, and I'm assuming now it's not a renormalizable theory in general, so the first thing I can do is, if I have a certain number of vector fields here, ij now will go from 1 to n, I can introduce a non-minimal coupling in front, meaning a matrix that depends on the scalar fields. Okay. And the same is true for the other kind of coupling I can have, which is the coupling between the field strength and the dual field strength. Which is essentially, so also this coupling R, this matrix R, is a matrix that depends on the scalar fields. And this is nothing essentially but the topological term. Now, this is a total derivative. This is the F wedge F piece in your Lagrangian, which is a topological term which you usually discard. But if there are scalars, then it becomes non-trivial, of course. Now, these are axion-like couplings, essentially. Then you might have couplings of this form. Of course, you might have additional functions of the various fields that you have in your theory, whatever they are, times, again, the field strength. And then I will have whatever else remains that does not depend on F. Okay. Now, of course, if I also have gravity, then I have fields all over the places, and I have to take into account as well. This is the generic structure I can have if I have a theory that has only the field strength of my vector fields. No, this is completely general. I'm not saying, I'm not giving any restriction. Well, of course, I would like this matrix to be negative definite if I want to have the correct sign of the kinetic term. But for the rest, I can forget. I mean, whatever it is, it is. These couplings can be anything I want. Now, the thing that I want to do is essentially see if I can extend this. This is the electromagnetic duality for a single vector field. Of course, if I have n on them, I could in principle do the same, because all these fields satisfy clearly the Bianchi identity because they are abelian vector fields. So dFi is always 0. And I can introduce, obviously now, some field which I call G tilde I mu nu. So the dual of G I can introduce in this way as the variation of my Lagrangian with respect to Fi mu nu. Okay. And if I do that, the equations of motion are nothing but the Bianchi identities of these fields, of these field strengths. Okay, so I introduce the dual field strength exactly like I did here. The only difference is that here it's trivial. No, you see, if from this Lagrangian and I do the variation, no, I do the variation of L with respect to F, I get minus 1/2 F mu nu. Then if I multiply by a factor, then you see that my G tilde coincides up to a sign with tilde. Okay, so this is a natural definition for the dual field strengths. So these are what I will call from now on G actually are my dual field strengths. And the Bianchi identities and equations of motion of my theory now have exactly the same form. So once again, you see that in principle, if I take these curvatures Fi and Gi and I introduce some new curvatures by some matrix here acting on Fi, Gi, the new objects that I obtain here will still satisfy the same equations. Okay. So this means that I can start a certain set, if you wish, of electric fields and magnetic fields, and I can exchange them. And actually, I can exchange the various fields among themselves and still get the same set eventually of Bianchi identities and equations of motion. The physics will not. There is one point, though, that I should take into account when I'm doing this, because here it would seem that I can take any linear transformation, and if I have n vector fields, any linear transformation, any 2n by 2n matrix, no real matrix. Of course, I want them real because these field strengths were real. And in principle, if I have nv of them, I have nv field strength and nv duals, and this could be an arbitrary invertible relation. Of course, I want to go from my degrees of freedom to another set which is equivalent, so I want to be able to come back. But you see, the point is that S has to be restricted. It cannot be any arbitrary linear transformation. Why? Because I have a condition here. I have that I want that the dual field strengths are coming from the Lagrangian in this way. So when I mix them up, when I mix F and G in an arbitrary way, I have a new F prime and a new G prime, but I have to prove that my G prime are coming from the variation of maybe a new Lagrangian with respect to F prime. It is not obvious that this is so. No? I can obviously take an arbitrary linear combination and I still have the same set of equations. But who tells me that that what I now call dual field strength is really the dual of the original ones by means of a certain Lagrangian, of the variation of a certain Lagrangian? Well, this has to be checked. And this puts restrictions on the allowed transformations. And what I will show you is that this is true if this transformation is in the symplectic group. It's not an arbitrary linear transformation, but it must be a symplectic transformation. Magnetic duality for NV vector fields is a symplectic transformation between the field strength and the duals. And you see, I call this dual field strength because, of course, when I have this set of equations, I could always say, okay, I have that I solve this Fi in terms of some vector fields, and then these are the equations of motion for those vector fields. But I could do the opposite. I could say, well, I have this GGI equals 0, so I solve GI locally or in terms of potentials, dI, and then these are the equations of motion. So as you can see, what is or I could take, I don't know, let's say that I have 5, that I goes from 1 to 5. Maybe I take the first 2 vectors here, then the next 2 from the dual, and then the fifth from the original one. Any other linear combination, as I mentioned, no? Well, almost any linear combination. And still, the set of equations of motion and Bianchi identities is the same, so the physics should not change. But clearly, the way we represent physics changes. The Lagrangian is going to change. These transformations cannot be arbitrary, cannot be a linear transformation. They must be symplectic. I will show you momentarily why that is the case in a simplified version. And the other thing is the following. If you transform the vector fields, the field strength and the dual with some matrix, be it symplectic or whatever it is, the Lagrangian is not going to remain invariant. Okay, my requirement is that the Lagrangian transforms in such a way that the new field strength, the new dual field strength, is equal of the vector field strength from the Lagrangian. And you see the fact that I have an action on the Fs in general may mix also with an action of the same symmetries also on the scalars. No, you can assume, of course, in principle that those scalar fields are completely untouched by these duality relations, but it could be that the scalar fields transform as well, in which case you have the transformation of these coefficients and of these couplings here, which will change, and you have to understand how it changes. And this is very important in general for the physics that you get. One important fact is the following, that if you now add gravity to this, while you see you will have an action on strength and the dual, you will have an action on the scalar fields. If you have other matter fields like fermion fields, you might have an action on the fermion fields as well. So all fields will transform under duality transformations. Gravity will not transform. The metric will not transform under duality transformations. And the reason essentially is that if you look at the Einstein equation, when you start looking at the Einstein equation, on the right-hand side, you will have the stress energy tensor. So you will start having things like this. Well, mind the coefficients, but I mean, the structure is going to be like that. And if you write this structure, the one that you get from the stress energy tensor from your theory, in terms of the field strengths and their dual, I will not do that, but believe me, because it's a very important point anyway, you can prove that what you have on the right-hand side is invariant under these duality transformations. So why this is interesting? Because this means that the duality transformations that I'm going to introduce now will change, will mix the degrees of freedom, will change what you call electric, what you call magnetic. It may send something which is perturbative in one setup and something which is non-perturbative in another setup. It changes, of course, what you call electric charges and what you call magnetic charges. So when you look, for instance, at black holes, it will take a certain configuration of black holes which might have a certain set of charges into a black hole which has a different set of electric and magnetic charges. But since gravity is unaffected by this duality, the solution, let's say the black hole solution that you had in the original theory, will still be a solution also of the new theory. Which means that once you find for a certain set of charges a black hole solution, for instance, you can use duality to map it into another black hole, which has different charges, which you know is a solution of Einstein gravity coupled to vector fields with certain couplings which are dictated by this duality. So this means that you can study a whole set of theories all together at once and study different solutions and show that their properties are the same. Okay, you will have this. This has been heavily used in understanding black holes in supergravity and in string theory, and especially in computing then the entropy, in checking the entropy of the black holes. Is a very, because this means that rather than studying a generic black hole with all possible charges, you can reduce yourself at the study of a black hole with a certain number of charges. There is a minimal set to generate the most general one, but the minimal set which is going to generate the general configurations once you act with these duality transformations. If I know that, I don't know, a black hole with 5 charges is going to generate the most general black hole with all possible charges after I do a duality transformation, then there's no need that I study this complicated solution with all possible charges. I study the black hole with 5 charges. I analyze that. If I'm able to reproduce the entropy for that, then I know that I'm going to be able to reproduce the entropy for all the other black holes. Duality is an extremely important concept. Okay? Any questions so far? Okay. So now let me do a few calculations. I'll try to do it slowly and show that indeed these transformations are going to be symplectic rather than general linear. And the way I'm going to do it is the following. Now, you see, when I introduce the dual field strength in this way, I'm essentially introducing a variable, a dual variable for a given variable. Now, I have the variation of the Lagrangian with respect to the variable, and that I call, it's the momentum, if you wish, no, something like that. It's not exactly, I mean, these have indices. This is still the derivative, though, of some field, and then you introduce some other object, which I call G twiddle. So I can imagine that I can define, I want to imagine that I can define a dual Lagrangian, starting from the original Lagrangian, by essentially doing a Legendre-like transformation, meaning that introduce a coupling here between my original variables and the dual ones. And then, if this was depending only on f, I want to use on this transformation the solution that tells me how f is a function of g, and then this is going to be a function of g alone. Okay, so it's like the Legendre transformation, where the dual variables have been defined in this way, and of course then I would like that my original field strength would come from this dual Lagrangian by means of the variation with respect to the dual variables. And I should be able then to go back to the original Lagrangian by doing the anti-transform, essentially. Okay. Now, you see, if I have to guess what this dual Lagrangian is going to be, then the structure of the Lagrangian, since the transformations are linear, because remember that these duality transformations are linear on the fields, since this was that was quadratic in the field, I should get something which is also quadratic in the field. I will get some matrix A that multiplies the contraction of 2G, twiddle. Then I will have another matrix that I call B that contracts a G twiddle and a G. The same structure as here, essentially. No, here I had a certain matrix which I called I, another which I called R. Then I had some couplings that were linear in F, and now I will have some couplings, okay, that are linear with G tilde. And also here I will have some other Lagrangian that does not depend on the field strengths and depends only on the scalar or whatever else you have in your theory. Now, if you apply these two definitions, this to the original Lagrangian and this definition to the dual Lagrangian, then you can see what the expression for G and for F is. For instance, you find that G tilde is clearly the matrix I times F plus the matrix R times F tilde. This I hope is obvious, no? If I take the variation here of these fields with respect to F, I get a factor of 2, 1/2. I multiply by 2, so I get I times F plus R times F tilde plus the couplings O. And if I do the same thing for F from the dual action, then I get A G tilde with a minus, the B with a G, and these other couplings O. Okay. Now, though, you see, if you want to be consistent, you should be able to take G tilde from here, plug it in here. You can compute, of course, the dual of G tilde, which is G here, and you should get just F, obviously. So consistency tells you that these new matrices A and B, which I introduced here, these matrices A and B should be just a function of the original matrices I and R. Okay, because if I take G tilde and I plug it here, I do the dual of that and I plug it in here, I should just get F. I should get an identity, no? So consistency tells you what these matrices should be. This tells you, for instance, that the matrix A should be minus the matrix I plus R, I minus 1, R. So the relations are not that straightforward. You can check them, though, and it's not very difficult to check them. And these couplings O also are related to the other couplings in this way. And moreover, the Lagrangian, the dual Lagrangian, contains a part that does not depend on the field strength, which is the original one, plus the coupling of these operators O's, which do not depend on the field strength. Okay, it is what it is. The important thing, the important message here is you can define the dual field strength starting from your Lagrangian. You can introduce a dual Lagrangian so that the field strength are now the dual of the dual. And consistency, of course, tells you that what you write here in the dual Lagrangian should be a function of what you had in the original Lagrangian. Nothing too deep at this level. But why this is interesting now? Because now I can take and do what I wrote there. I can see what happens when I apply a matrix transformation. So imagine that so what I was writing, Fg prime is some matrix that acts on Fg. And now let's take this matrix to be a matrix in blocks like this. Oh yeah, I should have written these A's in a different way. I don't know, these are calligraphics. This is a B, calligraphic, whatever. I mean, this is not the A that I have there. Okay, bad name. Should have used different letters. Now, these are the blocks of my matrix S, A, B, C, D. And then you see the duality transformation tells me that if I do it at an infinitesimal level, the variation of my field strength is going to be my matrix acting on F and G. So this is going to be some matrix Aij acting on F plus B acting on G. And the infinitesimal transformation of G will be some matrix C acting on F plus D acting on G. Okay. So this is just writing down explicitly at the infinitesimal level what duality action is going to do to the field strength and the dual. It's mixing them. No, obviously, it's mixing them. And then what I do, then you see, since I have these relations, I can see what happens when I apply those transformations to this relation. And of course, this thing should remain, the condition should remain consistent. So let's take, for instance, the first relation that I have there. So then you see, I have that if I apply this, so I'm applying, these are the dualities. This is the definition. So if I apply duality to F, you see that I have that the variation of G tilde should be the result of course, applying directly this transformation, but at the same time, I can apply it on this. And now the thing is that I will have for sure the variation of the field strength but if I assume that the scalars are also acted upon by the duality transformations, then I have also the transformation of the scalars, and I have some signs wrong somewhere here. Okay, I have a typo in my note, which however is going to be crucial. There's a sign missing there, I guess. Anyway, yeah, let's hope. Let's see if I manage to bring it home anyway. So we'll have Ij, the variation of Ij times F. Then I will have the variation of R times F tilde. And then I have the variation of these couplings O. Okay. So on the one hand, I have this. On the other hand, I have what I get from this, meaning that I can replace, of course, if this is delta G, you see, I can just take the duals everywhere. And I can have, on the one side, I have this thing, and on the other side, I have that. So I have a relation, a linear relation between, on the left-hand side, the coefficients of my matrix, the blocks of my matrix acting on F and G. And on the right-hand side, I have, again, I replace delta F with AF plus BG. I replace delta F tilde with AF tilde plus BG tilde. So I get a relation where I have some F's and G's on the left and some F and G's on the right-hand side. And the final result should be, of course, an identity. I don't want this to be anything new, of course. And let me the details of the calculations, but it's essentially trivial. No, you just match. Okay, let me sketch it at least, but then without really entering into the details. You see, from there I would have something like Cij F tilde plus Dij G tilde, that should be equal to I, then delta F is A. So this is Ij Jk Fk plus Ij B Jk Gk. This is G tilde J. Then I have the other piece. I have plus R, and then I have I A Jk F tilde K plus R. Here I will have B with G. Now the tilde of the tilde gives a minus. Okay, whatever it is. Plus I have the transformations of the scalars, delta Ij F plus delta R F tilde plus delta O. And this should be an identity. How do I check whether this is an identity or not? Well, use once more the definition of G tilde in terms of F, so that I bring this expression into an expression of only F's and F tilde. Can further plug this in here. So I rewrite this in terms of F and F tilde, I rewrite this in terms of F and F tilde, I rewrite this in terms of F and F tilde. And the final result I get then is something that multiplies F, something that multiplies F tilde, and whatever remains. And the whole thing should be vanishing. No, it should be the same expression on the left and right hand side. So if I do that, what I get is that in order to make this thing work, the matrix I has to transform, for instance, in the following way. Let me just show you this. The important thing is that both matrices I and R have to transform. So the matrix I has to transform with D on the left. It has to transform with A on the right. And then you need an even more complicated expression with B and R. And another piece here that goes with R and B. Okay, and then you get something similar for R and for O. Let me not show explicitly the expressions. If you want them, you find them in my notes. That's not important. The important thing is the following. You get that the scalar fields have to transform in order to maintain the consistency of the transformation. And they have to transform in a very precise way. Not only, you now find constraint on these matrices A, B, C, and D. Why? Because you know from the beginning that this matrix I has to be symmetric. Because it was the coupling in the Lagrangian that I now erased. Yes, sorry. It was the coupling in the Lagrangian. No, we had in the original Lagrangian, we had Ij over 4 Fi Fj, and then Rij, and then again Fi F tilde j. Okay, so clearly, because of this structure, I and R are symmetric. And once you find the transformation rules, the fact that they are symmetric tells you that if you do the transpose, of course, you should get the same expression. But this is not going to happen unless A and D are related. And unless B and then C, you will find in the other transformations, satisfy additional constraints. And the constraints you find, which are essentially at in your original duality matrix that was written in blocks like this, you have that C has to be symmetric. Transpose. B has to be symmetric. And A and D are related in this way. And if you put together these conditions, these are precisely the conditions that tell you that the matrix S is symplectic, meaning that, well, this is the infinitesimal transformation. The infinitesimal transformation, so the, let me call it sigma, if the full matrix is symplectic, meaning that it preserves the symplectic matrix omega, where omega is the matrix, symplectic matrix like that, then you see that the infinitesimal condition is clearly that S transpose omega plus omega S has to be 0. And these are the conditions that you get. Okay, this is just simple group theory. The message, though, is the following, is twofold. The first is you can transform vector fields into dual vector fields. You can mix up actually vector fields with dual vector fields and still get the same physics. The set of equations of motion and Bianchi identities is the same. You can do it consistently, though, only if you take combinations, linear combinations, which are given by symplectic matrices. Okay, so if you do a symplectic rotation between the field strength and the duals, and therefore between the vectors and the dual vectors, then your theory gives the same set of equations of motion and Bianchi identities. Okay, that's the first statement. The second statement is that if there are no minimal couplings to scalar fields, the scalar fields have to transform under duality transformations. The couplings have to transform. They cannot be invariant. So this duality action has a non-trivial action also on the coupling, on the minimal couplings, and eventually on the scalar fields. Finally, the final message is, if you do this and you check after you do all these transformations, because now remember, these requests are for consistency on the duality relations. I never discussed the Lagrangian, and in fact, if you apply this transformation rule to the Lagrangian, you don't get that the Lagrangian remains invariant. You get that after you apply the transformations, let me do it at infinitesimal level, after you apply that matrix, that symplectic matrix of transformation on the field strength and dual field strength, the Lagrangian changes by a term which is proportional to G to C, and a term which is proportional to B. And you see now that this is very interesting, because tells you that you can actually split your group of transformations into what is called the electric group, and then you have the non-perturbative transformations, which are generated by the B transformations. Why do I make this distinction? Because you see, first of all, if you really do if you just take A, so if you just do a block transformation, so of course you don't mix them, that's the point. If you don't mix field strength and dual field strength, then it's not going to change. That's fine. If you mix them with an electric transformation, which is like this, because what I'm doing is essentially I'm calling electric the original vector fields and magnetic the dual ones. That's the usual name, because essentially you will have that associated to the dual of the field strength, you will have the charges, and essentially you will write electric charges for the electric field of the original gauge theory, and then the electric charges of the dual will be the magnetic charges. So that's why we call them electric vectors and magnetic vectors. This transformation, since it acts, you see, if you act on the vector Fg, this sends F into A times F. So it doesn't change the original Lagrangian, it just changes the dual vector fields. But the dual fields are not appearing in the Lagrangian. So the Lagrangian changes with this term, but you see, this term is a total derivative. Cij is a constant now, and this is just a total derivative. It's F wedge F. So any electric transformation takes your Lagrangian, and at most it changes it by a total derivative, which of course at the classical level is perfectly equivalent. Also the Lagrangian. So these are symmetries. So this subgroup here is a group of duality transformations which are also symmetries of your Lagrangian, either exact symmetries or symmetries up to a total derivative, which again, I mean, at the classical level, these are symmetries. When you introduce B, though, Lagrangian is not invariant. It changes, but it changes also in a bad way, because your Lagrangian that was originally written in terms of F now contains a piece that depends on the dual field strength, so on the dual vector fields. So this means that your final Lagrangian is not going to be written down in terms of the vector fields A anymore. It's a non-perturbative transformation, because you have to rewrite the degrees of freedom. Because you see, if you want to invert now imagine that you write down your vector fields AI, which are those whose derivative is Fi. The dual ones are the ones whose derivative is Gi. But now Gi for you in your original Lagrangian is something of the form Iij d of Aj plus Rij. Well, there are duals here somewhere, something like that. And now you see, if I want to write down Ai as a, I have to invert this relation, and of course this is invert because I have also scalar fields here. I have derivatives. So the thing that I end up having is a non-local expression of the dual vector fields in terms of the original ones. So what I'm saying is essentially that while you can have a generic symplectic transformation that leaves invariant the set of equations of motion and Bianchi identities, the Lagrangian changes and it may be heavily affected by that. You might go into a new Lagrangian where you really have to use different degrees of freedom. You cannot use anymore the original degrees of freedom. And therefore, you will have to use degrees of freedom that are adapted to magnetic charges rather than electric charges, for instance. And this is the interesting aspect, because you can exchange, indeed, exchanging electric and magnetic charges essentially tells you that you go from something which is perturbative in one setup to something which is non-perturbative in the other setup, and vice versa. Okay, and once again, this whole thing is true independent of supersymmetry, and it doesn't touch gravity. So when you look at gravity solutions, this is going to be a transformation that you can use in order to relate different solutions of different theories in principle. Yes. I'll get to that in a moment. The question was whether this affects n equals 2 supergravity, and that's exactly where I'm going to go. But also, there is more. It affects n equals 2 supergravity, not just because in n equals 2 supergravity you have the graviphoton, but it affects the couplings of n equals 2 supergravity to matter, because in the vector fields, in the vector field multiplets, you also have scalar fields. And therefore, these symmetries will act on the scalar fields and constrain the scalar manifold. Other questions? Yes.
Hi. Hello.
Yes, please. Well, first.
Okay.
Yeah, you from home. There is a question
okay.
also here, but I will do it later.
Okay. So when you talk about the duality and the transformation, so I'm not getting the way you state your statement that perturbative in one setup, transforming non-perturbative in another setup. Can you please elaborate on this?
Why something perturbative becomes non-perturbative in the other setup?
Yeah. Yes. The
point is that essentially, imagine that you write down now charges for these things. You know that well, now this is a billion, but anyway, imagine also, if you wish, you can extend it to something on a billion if you wish, or you can do it if you introduce effectively point-like charges. You know that if you have a certain coupling, okay, let's see. What do I still need of this later? Well, maybe nothing really. No, this maybe is the only one that I want. So first of all, the thing is, once you have these vector fields, of course, you imagine that you can couple these vector fields to the path of a certain particle, and sorry, mu. And of course, each of these will be coupled with a charge, which is going to be what we call electric charge. Okay. Now, the dual vector field, of course, will couple to the path of a particle by means of a charge, which is different, of course, which now I call it magnetic charge. Okay. Now, if you look at the magnetic monopole solutions, for instance, you see that in terms of the coupling, this goes with the inverse of the coupling, so it's non-perturbative. So the relation between the charge of the monopole and the charge and the electric charge, the original electric charge, the original coupling you had in your theory is non-perturbative. Let me put it directly from the field strength. If you look at the gauge field strength, and write down this a kinetic term in this way, with some couplings here, Ij. Now imagine that these are just the couplings. So this is it's a delta Ij, let's say, 1/4, and here you have the charge square essentially, or the coupling constant square. Let me write G square here, not the charge. Okay, whatever it is. Now you see that acting with these transformations, these transformations A and C. Well, let's forget the C, but let's look at the A. The A is just mapping the F's into the F's. It's just mixing up. If you look at this form, it's just mixing up the I's into themselves. So it's not doing anything. But if you start introducing B, which is the non-perturbative part, then you end up mapping coefficients in front into their inverse. I will show you, let me see. Let's see if I have a very quick example. an explicit example. If you take, for instance, I should have an example here. I wanted to write down an explicit Lagrangian so that you could really see this explicitly. Yeah, I need some time to find it, sorry. The thing is that this action acts also on the scalar fields, and what you see explicitly is that this action is going to be related to the exchange of the coupling. So if you have the axion dilaton, so if you have the theory where you have one complex scalar, like it happens in string theory, for instance, where the non-minimal coupling you have here in front of the scalar field is given by, oh, here it is. I have it. Sorry, I found it, so I can show it explicitly. Let me do it explicitly, so this becomes manifest. Okay, so take this Lagrangian. Here I have a dilaton. And I have, well, I can take just one. Well, anyway. And I have an axion. Okay, I should really take two of these. And here I have a sign actually. So anyway, it's not too important. You have a dilaton and an axion, and then you see the field strength, the strength of this interaction is given by the VEV of this dilaton. No, when you go to canonical kinetic terms, this is -1/4 g², f mu nu, and then you see that the value of g² is related to the VEV of e to the -phi. Okay. Now, when you do what I just told you, which is you apply the duality transformations in a consistent way, this transforms the f's, it transforms also the coefficients in front, which are these scalar fields here. And among the transformations, you have, do I have it in the infinitesimal level? Well, you can combine essentially the two into a complex combination, which is, again, the conventions. Give me a second. Where did I write it? This is, well, it's a combination of C. I think it's like that, like this. Let me see if I find it correctly. There are factors. Anyway, the combination is the axion and the dilaton, obviously, as you would expect. Just trying to see if the combination is the correct one or not. Yeah, actually, I did it the other way around here. So, okay, e to the phi plus IC. And the duality transformation matrix that I was writing down before acts essentially on tau, transforming it into a tau prime, which is A tau plus B divided by C tau plus B. This is now the finite transformation, not the infinitesimal one. Okay, so when you exponentiate this thing, clearly when you exponentiate this thing, you also have elements on the diagonal, no? But you see right away from here, for instance, that if B is different from 0, let's take, for instance, B equal 1, C equal 1, and A and D 0. This is an allowed transformation, which is like this. And this transformation sends tau into 1/tau. And since this is related to the strength of your interaction, this is telling you that you send a theory which had interaction that was given by by e to the minus phi into something which now has an interaction which is e to the phi. So if before it was perturbative, it will not be perturbative after the transformation and vice versa.
Yes, thank you.
Okay. The question here, yes. Dirac quantization. Well, at this stage, as I said, first of all, this is just classical theory. So here everything is classical. All these things are continuous. I'm talking about transformations which are symplectic real, not symplectic Z. When you consider indeed string theory, or even if you just consider your supergravity theory, you will have Dirac quantizations, and then this will be constrained and it will not be continuous anymore, of course, yes. But it's essentially affecting the fact that the group is not continuous, but it becomes discrete. But the transformations remain the same. The only thing is that all these matrices that I'm writing down will now be given by certain specific numbers because they are in the discrete version rather than the continuous version that I had before. Okay. Other questions? If not, then let me show why this now. Yeah. These Stanton configurations are fixed points. I'm not sure they're fixed points. Why do you say they're fixed points? Well, yeah, but the point is that the transformation, as I said, is not just electric field going. So you're not, yeah, okay. I think the correct answer is no, but I want to think about it. I'll answer tomorrow. Let me think about it. I don't want to see wrong things. Let's see now why this is important for extended supergravities, and in particular for n equals 2 then, because I would like to introduce some ingredients of n equals 2 to show you a few things about black holes. Okay, so in n equals 1, the multiplets that we have are the gravity multiplet. You have, in principle, the gravitino multiplet, which, as I said, you're not able to couple consistently to gravity. So it's a multiplet of n equals 1 supersymmetry, but it doesn't appear in supergravity. Then you have vectors, and you have spirals. When you go to n equals 2, clearly you have twice as many supercharges. And this means that, let's say that you start from a scalar field, you don't generate simply a fermion. In n equals 1, the best you can do is you take one supercharge, you the fermion, then if you square the supercharge, you get 0, so you're done. In n equals 2, you can introduce a second supercharge. So once you take the scalar and you act with a supercharge, you get a fermion, but then you can act with a second supercharge. And then depending on how you do it, you either go back to another scalar or you go to a vector field, because from the fermion you can generate a vector, of course. And you can do this in general for all the multiplets, and the multiplets that you get are now combinations essentially of the n equals 1 multiplets. So you have a gravity multiplet which contains two gravitini, 1, 2, and a vector field. called indeed a graviphoton, because it's a photon that sits in the multiplet with gravity. You can have gravitini multiplet, of course, but let me forget about those. You will have vector multiplets where you have, yeah, why did I put an I here? I don't know, this is a Gaugino. Here I will have instead 2 Gaugini, of course, for a given vector field. And I will have a complex scalar field, because I'm putting together this multiplet and this multiplet. This had a complex vector, a fermion, another fermion, and the vector. And this is my vector multiplet. Or I can have another multiplet which contains now 2 fermions and 4 scalar fields. In principle, you would say 2 complex scalar fields, and indeed, if you are in global supersymmetry, that's the case. But as I already mentioned a number of times, if you go to supergravity, you lose the complex structure, and they become 4 real fields. Now, what is happening here that is interesting? The thing that is interesting here is that you see I have scalar fields which sit in the same multiplet with the vectors. So the duality transformation that I showed you before must act on the multiplet in a consistent way, in the same way, on the same fields of the multiplet, which means that it should act, if it acts on the vectors, it should act on the scalars as well. And you see, since you know that, as I discussed a few minutes ago, in a theory, you have vectors and dual vectors, and what you use is more or less up to you. You can take different combinations. When I introduce such a multiplet, I should be able to introduce also the dual ones, which should have their own scalar fields, which, however, cannot be additional degrees of freedom. So they must be function of the original scalars that I had here. And this is what I train my scalar manifold. On top of the structure, now, if you imagine you have in n equals 1 a scalar manifold, imagine that you have a scalar manifold, Hodge scalar, of course, in n equals 1. Let's say that we started with a Hodge scalar. Now, the thing is that when I move from one patch to the other, if I'm talking now about these scalar fields, because now, first of all, you see I have 2 scalar manifolds. I have one scalar manifold for the vectors and a different scalar manifold for the hypers. Okay, so let's talk about the scalar manifold of the vectors. Then this will have a structure which is different from before, because on top of the fact that if I have a scalar potential here and a scalar potential there, the two should be related as before by the real part of some holomorphic function. The thing is that now you see the scalar fields are part of a multiplet together with the vectors. And this means that this duality action that you have on the vector should be an additional structure that you put on top of your scalar manifold. So in n equals 1, you have a scalar manifold, which becomes Hodge scalar, because on top of the scalar manifold, you put a line bundle, and you know that the superpotential is a section of this bundle. The fermions are sections of the principal bundle that comes out of that, and they transform all when you do scalar transformations. Here, you will have that on top of this, you should have a symplectic bundle, because you know that whenever you have a certain number of vector fields, they should mix with the duals. And hence, since the scalars are in the same multiplet as the vectors, also the scalars should transform. Moreover, the structure changes when you go to from global to supergravity. Because in global supersymmetry, you see you have one scalar per vector. In supergravity, you have one more vector than the number of scalar fields. In supergravity, n equals 2, of course, the symplectic group that acts on the vector fields is 2nv plus 2r. Because you have nv vector multiplets plus 1 graviphoton. So the duality group acts on all these vectors, mixing them up. And this is also interesting because you start by considering the photon and the vectors as different fields. But duality mixes all of them up together. And now the number of scalar fields that you have cannot be as many as the vectors, because you have one less, because you only have nv scalars. So this means that you have to use new coordinates, which are projective coordinates. So Zi will have an I that goes from 1 to the number of vector multiplets, whereas the capital I goes from 1 to nv plus 1, because it runs, it's the same index that you have on the vectors. No, if I have my vectors, a mu I, have an index I that goes from 1 to, well, if you wish, from 1 to nv plus 1, or it's customary to use the 0 for the graviphoton. So this means that the scalar manifold will be described rather than by the coordinates themselves, by projective coordinates. So they are redundant, of course, depend on one less coordinate. And as I said, there must be a symplectic structure. So this means that on top of these holomorphic functions, if you wish, because you have to preserve supersymmetry, of course, so these are still functions of the original complex coordinates, you have to introduce also some dual projective coordinates in such a way that when you go from one patch to the other, it's the full set. So let me call it Z. So now Z is the set, the full set of coordinates xi, fi. These are projective, remember, so they are redundant. When you go from ZA to ZB, these are going to be related by a symplectic transformation. And moreover, since the Kähler transformation is acting non-trivially, you will also have a residue of this holomorphic transformation in this transformation here, again, suppressed with the Planck mass, of course, because in the rigid limit, this is going to disappear. So the structure becomes much more constrained, much more constrained. And it's very interesting because this means that you have this symplectic structure everywhere, and therefore the terms you will have in the Lagrangian will be written in a way that should be at least symplectic covariant, so that the set of equations of motion and Bianchi identities that you get from your theory are going to be invariant under symplectic functions. And this thing is going to happen even more if you raise the number of supersymmetries, in the sense that if you look at n equals 4, then clearly you start having 4 gravitini. Now A goes from 1 to 4. Then you will have a number of fermions here, which is, this is antisymmetric, so this is going to be 6. And then you will have scalar ABC, which are 4 scalars also, ABC. So this is 4, 3, 2. Yeah, this is 4. And then for the vectors, you will have 2 Giannis, and you will have 6 scalar fields. And that's all you can have. So you will only have a gravity multiplet and a number of vector multiplets. And if you end up in n equals 8, you end up with a unique multiplet which contains 8 gravitini, 28 vector fields, 56 spin 1/2 fields, and 70 scalar fields. So see, the scalars, higher supersymmetries, are always tied together with the vector fields. So this symplectic structure and these duality transformations will constrain heavily the nature and the structure of your scalar manifold. So, question on this? So if you look at n equals 2 supergravities in particular, now let me just introduce simply the ingredients without giving any more proofs. In n equals 2 supergravity, what you can do then is to define, where did I put it?
Hi, hello.
Yeah.
So why did we call Z as a projective coordinate? I mean, projection to what?
The xi are projective coordinates.
Yes, xi, yeah.
Because, as I said, they depend only on nv coordinates. And in fact, you generically are able to introduce what are called normal coordinates, which are simply the ratio of xi over x0, as you would do for a projective manifold. Then there are subtleties, because precisely because of this duality transformation, there could exist frames in which your x and f are mixed up in such a way that you cannot do any more of this, in such a way that the xi are not independent. You see, the important thing here is the following. You have nv plus 1 projective coordinates originally, and you have the nv plus 1 dual. Okay? These are all functions of the scalar fields. Symplectic transformations, duality transformations mixes them up. Originally, you must have the possibility to recover your coordinates, and one way to do it is, for instance, to introduce scalar fields in this way. So you take your holomorphic functions and you take this ratio. However, after duality transformations, it could happen that the xi that you're left with are not independent, because obviously the xi must be projective, but you have to have at least nv independent combinations. The fi's obviously must be redundant, so they must be functions of the xi. Okay, so if I don't want to introduce too many degrees of freedom, I still have nv coordinates. So the xi are going to be projective coordinates. So I will have only nv degrees of freedom in there, complex. The fi should be the functions of the same degrees of freedom. So the fi's generically, well, I will discuss it now, will be functions of the x. And by means of the definition of x, they will be functions of z. However, when you do a symplectic transformation, what could happen is that the independent degrees of freedom are a bit in x and a bit in f. So you might end up having xi, which are still your coordinates on the manifold, which are not really projective coordinates anymore, because you cannot take this thing in a consistent way, this ratio in a consistent way. I don't know if I answered the question.
Yes, thank you. So the symplectic transformation mixes the scalars and the vectors in a multiplet. So in
the
a
symplectic transformation requires that you have also these Fi's. Of course, these Fi's in principle are dependent on the X at the beginning. Then after the symplectic transformation, they mix up and then you don't know what happens.
Okay, so that
but you
means
will have at most n scalars, independent scalars, obviously.
I mean, does it mean that the scalars transforming into vectors and vectors transforming into scalars?
No, 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 no.
Yes,
no, no.
yes, that's why I'm confused.
There is no mixing of the vectors with the scalars. What I'm saying is that the same symplectic matrix that acts on the vectors acts also on the scalars. So what I'm saying is the following. When you're taking your field strength and the dual field strength, you know that you have a symplectic matrix, the duality matrix, that mixes them up, and the equations of motion and Bianchi identities do not change. When you do this, though, you should also take your coordinates essentially and mix them exactly with the same transformation. But I'm not, sorry, it's now I understand the confusion probably. Sorry, I should have used a different, this is a different F, this is not a field strength. This is a function of X. These are functions. These are the field strengths, and these are functions. I'm sorry. You know, in papers, you use calligraphic symbols. On the blackboard, it's a bit more difficult to distinguish them. Is it clear now?
Yes, yes, thank you, thank you. That was a confusion, yes.
Okay, sorry. So just to close, the n equals to supergravity then, for what concerns the vector multiplets, because I will focus only on the vector multiplet sector tomorrow, is described by a special Kähler manifold. And a special Kähler manifold then is NV dimensional Hodge-Kähler manifold, where, however, I have an additional structure. I have a tensor bundle given by the product of a holomorphic vector bundle with a symplectic bundle, with a symplectic structure group, sorry, and a holomorphic line bundle, such that, as I said, you have on a patch, you have certain coordinates Z, these coordinates, these are the Zs. These are related by means of a symplectic transformation and a holomorphic transformation in this way. So SAB is a symplectic 2NV plus 2R matrix, and HAB is holomorphic. So that the Kähler potential transforms. And in fact, now the Kähler potential is written by minus the log of the symplectic product of Z with Z bar. So here, what I mean with this notation, AB, this is the A transpose omega B, where omega is the symplectic matrix that I wrote before, 0, 1, minus 1, 0. So the Kähler potential is not arbitrary. The Kähler potential is not arbitrary because you want that this holomorphic transformation on your section results into a Kähler transformation. And of course, you don't want the Kähler potential to change when you perform a symplectic transformation. So it's a symplectic invariant quantity. And then there are some more technical constraints. which are, well, there's an additional constraint, which is the fact that if you take the symplectic product of the derivative of the covariant sections, which I can define now, this has to be 0. So you can define V, which is e to the k over 2 times z. So this is holomorphic. This is not holomorphic anymore. So when you take derivatives, you have to take the covariant derivatives, so the scalar potential, and you have to have this top of the rest for consistency of your action. And of course, you want the usual thing, which is that if you have 3 patches, A, B, and C, the product, of course, SAB, SBC, SCA should be the identity. Now, of course, you want to close this, the transition function should close. Okay, so now forget about this technical constraint thing. Supergravity for what concerns vector multiplets is still described by a Hodge-Scalar manifold, but of a restricted type. And the restriction has to do with duality. The fact that duality acts on the vector fields tells you that it should act on the scalar fields of the vectors. And generically, since you have one more vector than the number of vectors in the vector multiplets, you will have to use projective rather than standard complex coordinates. You will have to introduce the dual of those, and you will have that the scalar potential is given in this fashion. Now, one last thing, because this might be of interest for many of you that maybe look at this from string theory point of view. You can prove that given any such a manifold, you can find a frame in which these Fi are the derivatives of what is called a prepotential, since this was mentioned the other day. This is also called the prepotential, but this is the n equals 2 prepotential, which has nothing to do with the prepotential, of the killing vectors, which essentially dictates everything, all the couplings in your theory. That's why it's so important. You can define for n equals 2 supergravity coupled to vector fields by means of this function. Because once you have this function, you define the Fi's in terms of x. Of course, here you are assuming that the x are good projective coordinates, okay? So that you can introduce the normal coordinates that I mentioned before. Okay, so x, these are allowed, otherwise this is not going to work. But this means then that the scalar potential, since the scalar potential is going to be the symplectic product, which means that it will be, the scalar potential is going to be minus log of, what is it now? I x bar Fi, might have gotten the sign wrong, but I mean, this is the structure. So from F, you define Fi by taking the derivative. This defines the scalar potential. You take the derivatives, you get the metric. The couplings are all going to be fixed by that. However, while any theory, you can find a frame where this is true, after you perform a symplectic transformation, you can find frames where this relation cannot be true. So while the prepotential can exist in a certain patch, in a certain set of coordinates, it can also be that on another point on the manifold, it does not exist. It's not a global property. Again, these are defines patch, patch, patch. And since, as I said, when you move from one patch to the other, you use symplectic transformations, you might get a symplectic transformation that tells you that the Fi's are not anymore derivatives of a function. And what this might seem curiosity, well, first of all, it's important because string theory allows you to compute that F. So what happens when you are in a frame where that is not true? Well, You have to find what is the transformation that brings you to that frame, because this means that in the frame where you are, you cannot use string theory directly to compute that. But the other point is that is extremely important is that if you look at this theory doesn't have a scalar potential as all extended supergravities. While in n=1 supergravity, you can introduce a potential from the superpotential and then also from the gauging. In extended supergravities, there is nothing like the superpotential. The only way to introduce a potential is by means of the gauging. And if you want to break supersymmetry from n=2, you can in principle imagine that you can break it to n=1 and to n=0. The thing is that if you do it with an electric standard gauging and you are in a frame where there is a prepotential, you cannot break supersymmetry to n=1. There is no partial supersymmetry breaking unless you are in a frame where that prepotential does not exist. So the fact that the prepotential exists or does not exist is not just a curiosity. It's a crucial fact that allows you to either break partially supersymmetry or not in supergravity by means of an electric gauging. Okay? So, summarizing, we have seen today duality transformations. I insist on the fact that this is a feature that has nothing to do with supersymmetry. The whole first part of my discussion was just vector fields in 4 dimensions. There is not even a need of coupling it to gravity. Then if you couple it to gravity, it's interesting because gravity is invariant under these transformations. And this means that you can change your Lagrangian and get solutions to different Lagrangians which have the same physics, which are mapped by duality transformations. Then when you look at extended supergravity, since in extended supergravities you have the scalars are in the same multiplet with the vectors, this duality becomes crucial because it restricts the scalar manifold, because it introduces a different structure on the scalar manifold. You will have that these symplectic transformations will have to act on your scalars in some way. And in n=2, this is described by means of these projective coordinates, which transform not only with holomorphic functions, but also with symplectic transformations in such a way that the scalar potential remains invariant under symplectic transformations, and in such a way that if you have a prepotential in a given frame, you might not have it in another frame. And this has important implications for physics. Now, what I will do tomorrow is to take n=2 and look at the ungauged theory, so no gauging still, but to look indeed at black hole solutions. So I'll try to see how you can build a black hole solution that is supersymmetric or one that is non-supersymmetric. What are the differences? And again, this symplectic duality that we have here will play an important role, as I said already, and as I mentioned already, in classifying such solutions and in allowing us to find what is called the seed solution and study the seed solution, the solution that has the minimal set of charges which generates everything else. And this is the thing then that you want to construct in string theory, no? Because these black holes generic will be brane configurations wrapped. n=2 supergravity, for instance, comes from Calabi-Yau compactifications of string theory. So if you are now either you are type 2A or type 2B, you will have different types of branes. Let's say that we have 0 branes, we have 2 branes, we have 4 branes, 6 branes. Now, if you, well, a 0 brane is a point. If you take a 2 brane and you wrap it 2 cycle, you get again a point from the point of view of 4 dimensions. You take a 4 brane, you wrap it on a 4 cycle, you get again a point. So all these things become point charges in 4 dimensions. And if you look at the solution generated by these overlapping branes in 4 dimensions, this is essentially a charged black hole. And therefore, if you want to study the entropy of the black hole and explain the entropy of the black hole in terms of string theory, you want indeed to explain it in terms of the degrees of freedom of these branes, of this set of branes that produces those charges. The generic configuration is a mess. You will have these D2, D4, D6 branes, And imagine to study such a thing in string theory is very complicated. However, if you now know that by means of these duality transformations, the seed solution, the black hole that has the minimal number of charges, is a certain number of charges, a certain specific configuration of D2 and D6 branes or whatever, then you study that minimal configuration. You explain the entropy for that, and you have explained the entropy for any black hole in that theory. Okay? So that's the game that we're going to play tomorrow. Yep. When you have a manifold, as usual, you can cover the manifold with different, you will not be able to cover genetically. I mean, there will be manifolds that will have a unique chart, but you will have manifolds in which you have different charts. And there might exist patches in which you're not able to find the coordinates such that the prepotentials exist, yes. Such that I have a prepotential. Again, I'll answer also to this tomorrow. I want to think about it. Yeah. No, you're not changing theory. That's what I'm saying. That's exactly the point. So the theory is the same. That's what I'm saying. So the thing that the beauty of it is precisely this, that now you have more structure. So this means that your theory is defined precisely by all these transformations together. This is the beauty also in theory, no? In string theory, you don't need that, you don't have anymore the standard differential geometry because you have T-duality, for instance. You can talk which have the inverse radius, and still string theory goes smooth, doesn't see any difference because of T-duality. Here is the same. Now you patch your manifold with all these transformations. So your theory is defined in this way. It's not a different theory. Any other question?
Hi, I have one question. So because of the underlying symplectic structure, the Kähler potential is restrictive. So that's why the name suggests the spatial Kähler, or is there any other technical reasons?
The space is still Kähler, but it's special Kähler in the sense that the Kähler potential has to have this form. It's the logarithm of this symplectic product. So you cannot have something which is not the log of something here, for instance.
Okay. So because in the supergravity literature, there are other two types of geometry appears, that is very special geometry and the projective special, sorry, the projective scalar. So what's the basic distinction between a special geometry and a very special geometry and a projective scalar?
No, what is called a very special geometry is the scalar manifold of the vector multiplets in 5 dimensions, which are real.
Okay.
You don't have complex geometry there. A very special manifold is real. I mean, you're in 5 dimensions.
Okay.
It's not this. Yeah, it's different. Essentially, the additional for each scalar you have in 5 dimensions, when you go to 4, you get an additional scalar field from the reduction of the vector in the vector multiplet. No, you have a A5 component, the 5th dimension, the 5th direction of your vector, which becomes a scalar in 4 dimensions, and then each real scalar becomes a complex scalar, and then you get a special Kähler manifold rather than a very special manifold.
Okay.
Okay. Okay, I'll see you tomorrow then.